it turns out that this trace formula is something that it's all over physics and mathematics, kind of every place. It has different names. You know, it might be called zeta function or something, or some kind of zeta function, etc. The history is just great. It starts with three things where people don't talk to each other, period. I mean, they have no reason to talk to each other. One beginning is Euler, who did it all, but it's called Riemann zeta function, because Riemann made a conjecture made a hypothesis about the zeros of Riemann zeta function. So there is a part that has to do with number theory and counting primes. So, you know, what do we care about counting primes? We are happy to count to 3 in physics. Why should we care about counting primes? Then there is a very, very long history, because it turns out it's the big outstanding problem in mathematics to prove Riemann conjecture. And it's not a silly problem, because it's extremely fruitful problem. I mean, lots of good theory, lots of good mathematics has come out of it. I mean, it's not, you know, amazing amount of good mathematics. And one version that's very close to what we do in dynamical systems is a mathematician called Selberg in Trondheim during the war, 1943, etc. During that war, he had lots of time. People in Trondheim, turns out, have lots of time to think, sit and think, because the weather is incredible most of the year. He decided, if I can solve the zeta function, which is an issue about lattice of integers in one dimension, let me do it on a lattice in 2 dimensions. And then he did something called Selberg zeta function, which is very inspirational for us. Which you see, studied dynamics on 2-dimensional discrete lattices, and he proved the equivalent of Riemann conjecture. Now, we don't know still how to prove that one, but the fact that he proved it in 2-dimensional case is extremely fruitful and is very closely connected to quantum chaos. So what happens in the quantum mechanics of classically chaotic systems. So that's one example. So there's, you know, a huge tree of knowledge coming this way. Then there are people like Poincaré and Birkhoff, and, you know, and it kind of comes to, in modern times, come to David Rouelle, who is a Belgian mathematician working in Paris, and he wrote a zeta function, which is sort of, I'll derive it today, which is kind of approximation to this thing. And that was done thinking about foundations of statistical mechanics. So that's a thing about what happens when you're trying to make statements about entropy, about this and that in statistical mechanics. And then there's a third branch, which is quantum mechanics. So people who do quantum mechanics couldn't care less about people who, you know, make satellites and stuff, because, you know, that's for engineers. They don't care about classical mechanics. They do quantum mechanics. So there is a man called Martin Gutzwiller, who comes from Basel. In Basel, people collect all books. So he collects science books, like 2nd edition of Principia or something, and some expensive books like that. And as his hobby, he does celestial mechanics. But he's a quantum mechanician. He worked for IBM to study properties of gallium and silicon, because people have to make semiconductors. And he realized that he can generalize Bohr-Sommerfeld quantization and use WKB to something that's called Gutzwiller trace formula. So these 3 groups of people don't talk to each other, and they still don't talk to each other. I mean, so they're kind of very respectful. Rouelle is convinced, I know them all, they're living ones. So Rouelle is convinced that what Gutzwiller has done is unrelated to him, and it's some kind of fuzzy thing physicists do, you know, it's not rigorous. Gutzwiller is convinced what Rouelle did has no relation to what he did, etc. But he likes Selberg, so he thinks that to do. And mathematicians, of course, don't care. They do whatever they do. The amazing zeta function guy will show up on Thursday. There is a man called Zagier, who is very quietly announced in math seminars. Now, when I was an undergraduate, I, you know, got my undergraduate degree at MIT, but this guy got his PhD, and I think he was younger than me. So, you know, he just kind of went through MIT like meteorite. And he's a brilliant mathematician, and he has his own zeta functions, which are totally amazing. The zeta functions are very important for modular domain, etc. So these subjects are very much alive.